we're going to look at how the second derivative relates to this thing called concavity. And we are following the learning goal, understanding the concepts of concavity, points of inflection, and their relationship with the second derivative. Looking at what we know already, if we have some variable y, which is a function of x, we know some things already about the first derivative. So it's the rate of change of y with regard to x, in this case. And what else do we know? We know that graphically, we know that it's called the gradient function. The gradient function, it's about the story of gradients at points on the curve. If the first derivative is positive, we're talking about a curve that's going up. If it's negative, the curve's moving down. The gradients are negative, in other words. So if we're talking second derivative, we're talking about the rate of change of the gradient function. Okay, all this stuff here over on the left, it's the rate of change of all that. So the rate of change of the gradients, or in fact the gradient function. So it's how the gradient function's changing. So that means it's the rate of change of all of the infinite number of tangents, and if it's positive, the tangents or the gradients, it's the gradients of the tangents actually, isn't it? It's the gradients of the tangents. So if it's positive, the gradients of all those tangents are increasing. If it's negative, the gradients of all the tangents are decreasing. So we're going to see all the possible shapes and the characteristics of that, and you'll see the second derivative will appear in them. Now this video is not going to cover what's called the second derivative test. That's in the next video. So we can see the first shape here, and it's got a stationary point down there, SP, stationary point, and that stationary point is a local minimum from our previous work. Okay, and that is described as concave. This is concavity thing, concave up. Alright, so the concave part is facing up. Sometimes, not very often, but it's called convex as well, but you don't have to worry too much about that, I suppose. The first derivative, dy dx, is increasing. Okay, so you can see that by the curve itself is in blue there. Hopefully you can see that under all those tangents. And all these red tangents, you can see that they're taken there and they're actually increasing. We can take more tangents than this, but this is just a sample of them. But you see how they're increasing? They were quite negative up here, less negative there, 0 there, a little bit positive there, more positive, getting more positive all the time. So that derivative is increasing. And the tangents are anti-clockwise. Okay, as you go along, the tangents are moving around in an anti-clockwise fashion if you have a look at all those red tangents. Now, for the second derivative, it's positive. So the second derivative is positive. Why? Because the rate of change of these is positive. If you go from something that is quite negative to up to 0 and then positive and then more positive, that's a positive change. So the second derivative is positive. So this d squared y dx squared is positive for a concave up shape. In the second shape here we have concave down. Okay, we have a local stationary point there is a local max. And we have our concave down, and therefore we have the opposite situation. Our first derivative dy dx is decreasing. It's the opposite scenario to what we just saw. So the tangents are going clockwise as they change. So we can see quite positive here, less positive, 0, slightly negative, more negative, quite negative. Okay, so that means the rate of change of those tangents, second derivative, is negative. The third out of the fourth shapes, I say shapes because these are all points of inflection, but there are a couple of different types I'm going to go through here. So this is called point of inflection. And I'm just going to refer to that as POI in this video from here on. And we've got several types. Now, one of the big features is that as you go along, so this is phase 1 here and same curve phase 2 here, it's very important that we can see that the concavity changes. That's important. The concavity changes, so it goes from concave up to down, concave up to concave down, okay, or concave down to concave up. It could be either. Okay, so that's a key feature of a point of inflection. And dy dx switches between increasing and decreasing. So it switches. Okay, so on this one here, the first derivative was increasing. Now it's starting to decrease. It's still going up, but it's still positive, but it is decreasing. Okay, so switches between increases and decreases. Okay, the second derivative it equals 0 at the point of inflection. So the rate of change of the tangents is 0 there at the point of inflection. Okay, so this one here has a positive second derivative and then it switches to a negative second derivative. Okay, so that's the other feature. And the second derivative changes its sign. Okay, it could be from positive to negative or negative to positive, either side of the point of inflection. It goes from increasing 0 decreasing or decreasing 0 increasing. Notice the and there, it must do both. The last one is a particular type of point of inflection. This last curve, the horizontal point of inflection, a special case, is as per the one above in green. Okay, all those qualities are as per the point of inflection, but the point of inflection, the horizontal point of inflection itself, this point here or this point there, notice how there are two cases, but the horizontal point of inflection itself, this place here, is a stationary point. Okay, it's a stationary point. So it's got a gradient of 0 at that case there. Notice how the more general type does not have a horizontal point of inflection. The gradient is not 0 at that point, so it doesn't actually have, this type doesn't have a stationary point. This is a particular case down here of the horizontal, of the point of inflection, the horizontal one, so it does have a stationary point. Okay, so 3 out of 4 of these cases do have stationary points where the gradient is 0. Next video is going to be about the second derivative test to test this.